Hello everyone and welcome to my channel. This is the first video I put on my YouTube channel and it's about number bases and number systems. I hope you'll like it. Let's see the video and I'll be back. Hello again. At this video we are going to talk about number bases or number systems. Why do we need to learn number systems? Because we're going to deal with the digital world. As it's obvious from its name, it's something related to digits, and anything that's related to digits must also be related to numbers. There are actually four main number systems that we're going to need when we're dealing with the digital world. The first number system is decimal, which is in base 10. For example, we have 189 in base 10, or we can omit the parentheses and write it as 189. Another number system that we're going to need in the digital world is octal, which is in base 8. For example, we have 267 in base 8, or we can write it as 2670, which stands for octal. We also have hexadecimal. Hexadecimal numbers are base 16. For example, we have 3AF in base 16 or 3AF in hexadecimal. Another important numbering system is binary, which is in base 2. For example, we have a number here 1011 in base 2, or we can write it as 1011 with the subscription B, which stands for binary. Now let's start with decimal number system. Decimal numbers are base 10 numbers. We actually use decimal numbers in our everyday life. Digits in decimal number are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have a total 10 digits here. These digits are multiplied by powers of 10 to represent numbers. For example, we have 36 here, which is actually a 3 multiplied by 10 to the power of 1, which is tens, plus 6 multiplied by 10 to the power of 0, which is ones. If we want to talk about the fractions in decimal numbers, we have 0.29 or 0.29, which is a 2 multiplied by 10 to the power of minus 1, which is 1/10, plus 9 multiplied by 10 to the power of minus 2, which is 1/100. In total, we have the number 36.29, which is actually 3 multiplied by 10 plus 6 multiplied by 1 plus 2 multiplied by 1/10 plus 9 multiplied by 100. In decimal number system, if we want to count any further than 9, we need to have 2 digits to represent it, as our digits cannot represent any value higher than 9. Let's say we count up starting from 0. We go upper and upper until we get 9. If we want to count 1 unit higher than 9, we don't have any digits to represent it. So we're going to need 2 digits, which in this case we get to 10, which uses 2 digits to represent 1 unit higher than 9. The highest 2-digit number is 99. Let's say we count until we get to 99. If you want to go even 1 unit higher than 99, we don't have any digits to represent it with a 2-digit number, so we need to use 3 digits. To go any further than 99, we need 3 digits, which gets us to 100, or we call it 100. In displaying decimal numbers, we don't usually use subscriptions because decimal is the default system. So for example, 123 in base 10 is not very common and 123 is used instead. Let's jump to octal numbers. Octal numbers are base 8 numbers. Its digits are 0, 1, 2, 3, 4, 5, 6, and 7. We have a total 8 digits here. In base 8 case, we borrow digits from decimal and we leave 8 and 9 out because we don't need them. These digits are multiplied by powers of 8 to represent numbers. For example, 457.21 in base 8 equals to 4 multiplied by 8 to the power of 2, 5 multiplied by 8 to the power of 1, 7 multiplied by 8 to the power of 0, which is 1, 2 multiplied by 8 to the power of minus 1, which is 1/8, and 1 multiplied by 8 to the power of minus 2, which is 1/64. If we want to count any further than 7, we need to have 2 digits to represent it, as our digits cannot represent any value higher than 7. So as you see, in base 8, our digits can go up to 7. We don't use 8 or we don't use 9. We don't have them in base 8. So if we start counting, when we reach to 7, and if we want to go 1 unit further than 7, we need to have 2 digits. So 1 unit upper than 7 must be 10 in base 8, which has the actual value of 8, by the way, but it's shown as 10 because we are in base 8, which by convention is not called a 10. We shouldn't call this one a 10 because it's in base 8. It doesn't have the value of a 10. It's called 10 in base 8 or octal 10, and sometimes represented by 10 base 8. The highest 2-digit octal number is 77 in base 8. This is not 77. This is 77 in base 8. So to go any further, we need 3 digits, which leads us to 100 in base 8. However, it's not called 100, but it's called 100 in base 8 or an octal 100. And finally, because octal is not the default number system, if our number is in base 8, we must use subscriptions to clarify the base and avoid any confusion. For example, 5 for 7 in base 8 or an octal 6-3. Now let's jump to hexadecimal numbers. Hexadecimal numbers are base 16. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. We have a total 16 digits here. In base 16, we also borrowed digits from decimal. However, because a single digit must represent a value higher than 9, we need more digits. So we borrow letters A to F to represent the required digits. For example, A represents 10, B is 11, C is equal to 12, D represents 13, E is equal to 14, and F is 15. We have an example here. E3.2F in base 16 is equal to 14. You know, we have an E here, and E represents 14. So it's a 14 multiplied by 16 to the power of 1, which is a 16, plus 3 multiplied by 16 to the power of 0, which is 1, plus 2 multiplied by 16 to the power of minus 1, which is actually 1/16 plus 15 multiplied by 16 to the power of minus 2. And why do we have 15 here? Because we have an f here, and f is equal to 15. If we want to count any further than f, we need to have 2 digits to represent it. Because we are in base 16, the highest digit we can reach is f. And if we want to go even 1 unit higher than f, we need to have 2 digits to represent it. So 1 unit upper than f must be 10 in base 16, which is not called a 10. It's called 10 in base 16, or hexadecimal 10, and sometimes represented by 10 base 16. Similar to decimal or octal case, any number higher than ff in base 16, which is the highest 2-digit number in base 16, leads us to 100 in base 16, which also is not called 100, but it's called 100 in base 16, or a hexadecimal 100. And finally, because hexadecimal is not the default number system, if our number is in base 16, we must use subscriptions to clarify the base and avoid any confusion. For example, BFD with the subscription 16 represents that our number is in hexadecimal, or we can write it hexadecimal DA6. Before we jump to binary numbers, there is a small formula that we need to talk about. First, let's make a rule. If we take the base to be r, digits range from 0 to r minus 1 as coefficients. Coefficients are multiplied by powers of r to represent numbers. And this is the formula. A is the coefficient and r is the base. As you can see the formula here, A is the coefficient, r is the base, and n shows the place. Now let's jump to binaries. Binaries are base 2 numbers. Digits are 0 and 1, so we have a total 2 digits here. In base 2, we also borrow digits from decimal, obviously. If we want to count any further than 1, we need to have 2 digits to represent it, as our digits cannot represent any value higher than 1. So 1 unit upper than 1 must be 10 in base 2, which is not called a 10, it's called 10 in base 2, or binary 10. Similar to decimal or octal case, any number higher than 1 in base 2 leads us to 100 in base 2, which also is not called 100, but it's called 100 in base 2, or a binary 100. Alright everyone, this puts an end to the video. I hope you liked the video. Please leave your comments because I'd be very glad to read and answer them. I also need you to subscribe to the channel and turn on the ring bell because I need your support. And of course, I'm going to do my best to make great videos to everyone to learn. Thank you.